Good day, everyone. My name is Amy Lambert. I'm EA's Director of Communications. Welcome to the sixth and final webinar in our series as part of our 50th anniversary celebration. Now, I'd like to introduce today's speakers who will be discussing managing your organization's risk with regard to climate change. Dr. Dan Walker is a chapter co-author of the NCA 5 Climate Assessment, a founding member and past chair of the American Society of Civil Engineers Committee on Adaptation to a Changing Climate, and conducts research through the University of Maryland Center for Technology and Systems Management. Dr. Chris Anderson joined EA earlier this year as the National Service Line Program Manager for Climate Change. He is a climate scientist with more than 25 years of experience. John Coombe is a senior engineer and chief of EA's Environmental, Health, Safety, and Sustainability Compliance Services. And Jane Aaron has more than 30 years of experience as a project manager, architectural historian, cultural resources specialist, and National Environmental Policy Act specialist. Now I'll turn it over to Dan to get started.
All right, thank you, Amy, and thanks everybody for joining us today. I'm really excited to be here. I'm very pleased and honored to be leading such a distinguished group as we talk about what I think are really some of the emerging trends in climate change. You know, if you've been following events for the past year, you're familiar with the IPCC, the National Climate Assessment, and the discussions that are taking place in Dubai or wrapping up this week. You know, you've probably got a pretty good handle on climate change. But what we're going to focus on today, I think, is what I see as kind of like some of the emerging issues, some of the changes that I've seen in the last few years over how we kind of perceive climate change and its impacts and its implications for our clients. First of all, there's a growing sense of urgency. I think, as you'll see, and as you've probably noticed, the impacts from climate change are becoming more and more demonstrable. The rate of change is picking up. So we're really kind of at a critical point here. This is no longer kind of a theoretical in the future discussion. We are now dealing with issues today that we have to take some kind of immediate actions on. As a consequence of that, there's some emerging trends in policy and practice that I'm going to go over. And then I'm going to kind of try to set up a little bit of a distinction between site-specific and systematic approaches. Then I'm going to turn it over to Chris, who's going to talk about the science, especially some of the implications of the 5th National Climate Assessment that just came out. He's then going to kind of leverage that to go into a discussion of vulnerability and adaptation, including the emerging focus on nature-based solutions. He's going to then turn that over to Jane, who will talk about more of a portfolio approach, moving away from individual projects, but moving more into a kind of a portfolio approach, a systematic approach, especially leveraging some of the work that she's done with DoD. And then John's going to kind of take it and run with it and talk about how, you know, the long game here is mitigating the causes of climate change. Has always been an important focus, but all of the emerging impacts and the costs associated with those impacts are just adding a more urgency to the recognition that we have to deal with our carbon footprints. And then I'll come back and try to wrap things up a little bit. Next. So in my mind, what's really driving the discussion, especially with regard to adaptation to climate change, is the growing number of major natural disasters that are weather and climate related. This slide from NOAA, from the National Center of Environmental Information, shows a trend over the last 40 years in the count of billion-dollar disasters in constant dollars. So, you know, prior to 1980, the number of times that we would have a natural disaster, weather or climate related disaster, that exceeded $1 billion in losses was pretty rare. Over the last 40, 45 years, essentially, those have become all too common. In fact, last year was a record year with $25 billion disasters, and the total losses exceeded $600 billion. So this is driving a real significant push to become a more resilient nation. Part of this trend is undoubtedly what we build, how we build it, and where we build it, but it also reflects the changing nature of weather and climate systems. Next. The other kind of takeaway from this is these billion-dollar disasters take many different forms and affect many different parts of the United States. And that's a significant trend, I think, because in the past, these natural disasters tended to be focused along, the East Coast or the Gulf Coast, and were almost entirely hurricanes. Now we have billion-dollar disasters across the country taking all types of different shapes and forms. And so that has really driven an interest, not just in the White House or in the administration or in the risk and reinsurance industry or in the Department of Defense, but in Congress. Congress is responding to this next through a series of legislation going back a few years that were really focused initially on improving our ability to predict weather events that can lead to natural disasters. Much of this work, the Built to Last Acts, the Flood Acts, the Precip Acts, were really driven or really focused. Can you go back one? We're really focused on having the Department of Commerce through NOAA, the National Oceanic and Atmospheric Administration, and the National Institutes of Standards and Technology work with the standards of the engineering and building code standard setting bodies to improve the way that weather information is, especially for future conditions, is incorporated into engineering standards and building codes. That much of that work has now been funded through the Infrastructure Investment and Jobs Act and the Inflation Reduction Act. But what's really important is this is bipartisan legislation, especially those early acts enjoy very wide support across the real spectrum of senators and congressmen. Next. I'm very fortunate to be working with the American Society of Civil Engineers. ASCE has 150,000 members, but what's really germane here is ASCE is one of the premier bodies internationally that sets engineering standards, which find their way into building codes all over the world. ASCE recognized the need to step up and provide more information to practicing engineers to provide us with a more resilient nation. So they partnered with NOAA, the National Oceanic and Atmospheric Administration. Earlier this year in February, they signed a memorandum of understanding that's really focusing our ability to bring federal climate science, the best and brightest in terms of climate data sets, climate modeling, climate science, to improve the way ASCE develops its codes and standards. This has led to a very broad discussion of a whole range of issues around how the nation can become more resilient, including the role of nature-based solutions and other approaches, so that we're taking a more systematic approach to mitigating risk from climate change. Next. So I'm going to turn it over to Chris, who's going to talk a little bit about the National Climate Assessment, and then I'll talk to you again later at the end of the hour.
Great, thanks for teeing up the National Climate Assessment for me, Dan. And what I'm going to do is take a couple of the top level messages from the National Climate Assessment and explain them, and then I'll dig into a few of the specific risks that are highlighted in the National Climate Assessment within the context of site-specific projects. So the top message of the NCA5 is that change in weather and climate risk has been observed in all regions of the United States. Climate change is no longer a future consideration, it is a now consideration. It is a topic for projects being implemented today. The type of change, though, varies by region, and so NCA5 has provided an in-depth online data atlas to enable practitioners to explore and identify regional to local changes. So the images on this slide show some of the information available in the atlas, as well as a link at the bottom of the image that can guide you to the atlas. So why is the top message of NCA 5 really important for site-specific projects? Well, the message that changes already occurred is important, basically because of what Dan has indicated with the change in weather risk and how that has been realized in an increase in billion-dollar weather disasters. The cost of weather and climate change is relevant at the project scale because if each project does not consider ongoing changes in weather and climate risk, then the future cost could go well beyond the expectations of the project design. And so we've seen that trend in billion-dollar disasters. We could also see that trend at projects that are poorly designed. So the NCA 5 also uses an emerging risk perspective that could be incorporated into project planning. The NCA 5 conveys future changes with respect to global average temperature increase, and this is since the pre-industrial period, which is the late 1800s. For instance, on this slide, the NCA 5 Atlas shows the expected future frequencies for several risks: wildfire, river floods, crop failure, tropical cyclones, drought, heat waves, and they are all conditioned upon the global average temperature, with increases indicated for 2.7 degrees Fahrenheit, 4.3, and 6.3 degrees. The perspective boils down project risks to two very practical questions. For adaptation projects, the question becomes simply, what global average temperature is likely to occur over the project implementation lifetime? Whereas for mitigation projects, the consideration is this: what risk and potential costs can be avoided altogether by reducing carbon emissions to prevent global average temperature from reaching specific levels? So having it conveyed in this simple metric allows us to ask simpler questions to guide our projects. Next slide, please. To convey this temperature change perspective, the NCA 5 includes a stopwatch graphic, and it demonstrates when the global average temperature thresholds are expected to be exceeded. Here's the graphic for a 2 degrees Celsius global average increase above the pre-industrial temperature. 2 degrees Celsius, by the way, is 3.6 degrees Fahrenheit. The graphic shows that the exceedance is expected around 2050. And the way you determine that from this graphic is that the range of assumptions about the greenhouse gas emissions into the future determines how soon that threshold is reached. And so on the left side of this graphic, you can see the case under which the greenhouse gas levels increase almost unimpeded by policies and technology. The rightmost watch is the case of immediate greenhouse gas reductions, resulting in greenhouse gas levels becoming stable in the very near term. But the current GHG trend is in the range of the middle two watches, and you can see that the average time for when 2 degrees Celsius is reached in these two central scenarios is between 2047 and 2053. So what this means at the site level for projects is that weather and climate risk associated with 2 degrees Celsius warming is the expectation for design lifetimes of 20 years or longer. Next slide, please. So those are the two top messages to convey, that there's data available to use our project planning relative to global average temperature to convey our risk, as well as the changes in climate are occurring right now, and the risks are being experienced across the United States. What I'm going to go into are a few specific risks and demonstrate how vulnerability and adaptation are emerging as new technologies and implementation approaches at the project level. Next slide, please. So the processes and steps for vulnerability for incorporating climate change into adaptation depends on whether the project is at the stage of a climate vulnerability screening, a project design, or a project implementation. The guidance documents are much more widespread now than they were 10 years ago, and it's a great advance of research community and pilot study communities. These documents now show how to perform vulnerability screenings and adaptation planning, and typically these are distributed by federal and state agencies, as well as professional societies and nonprofit organizations. So vulnerability to climate and weather at a site or across multiple sites in a portfolio is a necessary first step to identifying effective adaptation strategies. The vulnerability analysis requires two pieces of information. One is the sensitivity of the site to change in climate, and the second is the expectation for what change is going to occur. Part of the sensitivity, that's a dimension that's important in a lot of cases, is the criticality of the site. This means what is the tolerance for any failure whatsoever of that site? Again, that idea and that assessment sits underneath the idea of sensitivity. So when performing vulnerability as well as adaptation studies, the type of information needed will need to be different. For vulnerability analysis, we can rely sometimes on expert judgment for sensitivity analysis, and we can rely on proxy data, climate and weather metrics, indices for project exposure. But at the design and implementation stage, the information and data requirements may become more stringent, and analysis steps may become more intensive. We have to often use formal definitions for metrics that relate to engineering tolerances, structural integrity, and usually have to have a broader inclusion of uncertainty analysis. And so the very first step of the vulnerability screening is critical for being able to prioritize the design stage, which is itself important for being able to design or inform the cost and benefit structure expected from when the when the adaptation solution is implemented. Next slide, please. So nature-based solutions are playing a big role as we look to incorporate adaptation into site-specific projects. Nature-based solutions are projects that are designed to protect, sustainably manage, and restore natural or modified ecosystems while providing benefits to people. Nature-based solutions are attractive for climate change adaptation and risk reduction for many reasons. Some of them are the following. Typically, nature-based solutions include some level of inherent resilience. They can become very flexible systems to build, incorporating many different design elements. They can be enabled in an adaptive management context. They often remain cost-effective, and they also achieve multiple co-benefits. There's sometimes around nature-based solutions, community development or recreation and economic opportunities. There's biodiversity development and also contaminant removal. And one of the contaminants that can be removed by nature-based solutions is greenhouse gases. And so at times, nature-based solutions can be both an adaptation and a mitigation. Nature-based solutions are garnering high interest and support across all entities supporting adaptation. And what I show next are three project examples that build from the NCA5 data and demonstrate for change in sea level, extreme precipitation, and drought, how nature-based solutions can be incorporated as risk reduction measures. These projects in particular are supported by an array of agencies and show new directions of effort, as well as new emphasis in several different agencies on nature-based solutions. Next slide, please. So NCA5 documents that change has already occurred in daily extreme rainfall. The NCA5 plot on this slide and available in the Atlas shows the historical change with several different approaches for measuring extreme daily rainfall. The percent change, as is shown here, is highest in the northeastern United States, and moving from northeast to southeast to central to west, the percentage change becomes smaller. Looking forward in time, when the global average temperature exceeds 2 degrees Celsius, percent change is predicted to be upward everywhere, except in the desert Southwest and some of the Southwest Intermountain. The largest percent change in the future projections is in the Northeast and Southeast, similar to what we see here in the historical. But there's a new area of high percent change at high elevation locations in the West and Northwest. This is reflecting a shift to fewer snow days and more rainfall days. Next slide, please. The extreme precipitation finding in the NCA5 will mean that any project that addresses extreme precipitation will need to include a climate change risk assessment. The common risks of extreme precipitation are listed on this slide on the left, And on the right-hand side, there are several nature-based solutions and natural feature approaches listed. So I will show the application of vulnerability screening to a contaminated site. Climate vulnerability screening for contaminated site projects is becoming more widely recognized and required. Some examples of climate change concerns include a change in landscape condition that could lead to contaminant exposure. There could be storm damage to remedies that could lead to compromised structural integrity. Or there could be, for example, water tables moving into higher layers of the soil and into soils that are contaminated. So next slide, please. This slide shows a climate vulnerability screening tool developed for several climate stressors and applied to hazardous waste site. I'm showing only the precipitation screening to stay within our time limits. The screening tool enables a qualitative directional analysis as a first step within the remedial investigation and feasibility study phase. Screening tools can also be applied during 5-year review or optimization studies. This screening tool incorporates climate risk within the site-specific elements, including geography, geology, land cover, current and historic land use, political and cultural norms, and other factors that you could consider that are important to the site. The 2 elements of the vulnerability are shown in this matrix. Those elements, again, were the sensitivity to climate change and the exposure to climate change. And in this matrix, they're evaluated qualitatively as high, moderate, or low risk. This results in 9 combinations of sensitivity and exposure, and the tool summarizes the 9 combinations in a square matrix with coloring to differentiate cells with low and high risk. So after completing the screening activity, the project team is able to visualize and to prioritize the candidate solutions for the design phase. Next slide, please. So I'm moving into sea level rise. The NCA 5 shows along the eastern United States coastline, and the Gulf Coast an upward trend in sea level. These trends in this region exceed the global average upward trend. Since 1990, the total historical increase in sea level for these 2 regions ranges about 6 inches to a foot. But looking forward, by mid-century, when global average temperature is likely to exceed 2 degrees Celsius, the upward trend is expected to accelerate. In these 2 regions in particular, sea level is expected to rise a minimum of an additional foot to as much as 2 feet. Next slide, please. This historical trend in sea level reported by NCA 5 means, again, just like extreme precipitation, that any coastal projects will need to include a climate change risk assessment. Some coastal risks are listed on the left-hand side of this slide, and nature-based approaches to addressing the risk are listed on the right. It's clear that in the United States, there's vulnerability to sea level rise along the coastline, but the level of adaptation is not as certain because there's a wide range of sea level rise expected. Nature-based solutions and gray-green solutions are advantageous when dealing with uncertainty because they can enable flexible design and they're amenable to adaptive management. And this means projects can proceed incrementally. So next slide, please. An example of design flexibility is a cold region project in Point Hope, Alaska, which is in northwestern Alaska above the Arctic Circle on the western tip of the Lisburn Peninsula. So according to NCA 5, this region's sea level trend is outpacing the global trend. The Point Hope project illustrates flexibility needed and enabled by using natural features and traditional ecological knowledge in adapting to climate change. The site is located only 13 feet above mean sea level, and the location is already experiencing effects of sea level rise that include coastal erosion, ocean encroachment on infrastructure and historical sites, and shifts in wildlife patterns that alter food systems. So this project started with engagement with the Inupiat community, and the Inupiat community pointed to steps they had already taken to create makeshift coastal defenses, but they were concerned that the defenses were insufficient to protect their traditional sod houses as well as historic ice cellars containing grave sites and ancient ruins. So in addition, this community provided direct evidence through traditional ecological knowledge that informed the quantitative modeling of beach dynamics, and it motivated further data collection for monitoring. So after engaging the community, the analysis came up with 7 preliminary alternatives for design consideration. And they used the criteria to select the final design that included things such as community acceptance, the maintenance of the remedy, the use of natural and nature-based features, the cost, and the effectiveness in slowing or preventing erosion. And so the final design you see here envisions a revetment with also including reestablishment of dunes and revegetation with native species. So in addition to all this flexibility, working with the local community and gathering knowledge from them, the project required flexible partnering and funding sources as well. In addition to these community partners, research organizations had to support some non-traditional approaches to integrating local knowledge with and the inherent uncertainty of the climate projections, leading to interpretations that maybe didn't have an equation. They also had to support research monitoring because these are new practices and new systems being installed in a cold region. And we needed to have the monitoring in place to understand their efficiency and how well they would hold up against the encroaching ocean conditions. So the outcomes of this project, though, through all this effort and flexibility, will contribute to building more confidence, we believe, in funding future projects in this region, where project funding historically has been limited by lack of information on implementation outcomes. So next slide, please. So the final climate change risk I will discuss is drought. NCA 5 documents 3 expectations for future drought. By mid-century, when global average temperature is likely to exceed 2 degrees Celsius, the characteristics of drought in the United States are expected to be the following. First, the drier regions and the drought periods will become hotter, and that causes larger annual water deficits as plants and humans consume more water to mitigate the added heat. Second, dry regions will expand along their periphery as storm systems shift northward. Alliteration, huh? Third, the difference between wet and dry years will be larger. This means that the swing from a flood to a drought will be much more severe than it has been in the past. Next slide, please. This slide shows on the left-hand side some risks that could be altered by changes in droughts. And on the right-hand side, the slide lists gray, green, and natural approaches to mitigating drought risk. Because, as I discussed earlier, the severity of drought characteristics are expected to change over the next 25 years. That means that projects for water, landscape, and habitat will need to include a climate change risk assessment, but it also means that the implementation may benefit substantially from adaptive management. So towards that end, I illustrate a project where we have an adaptive management approach built into it from the outset. Next slide, please. So this is a managed aquifer project. Managed aquifer recharge is the purposeful recharge of water to aquifers for subsequent recovery or for environmental benefit. And it's being seen widely across the globe as a key component to groundwater management and becoming necessary to ensure groundwater resources remain reliable for generations to come. Managed aquifer recharge may develop solutions incrementally, and that's one of the advantages of using this gray-green technology. It can enable monitoring and review of project priorities under changing social demands, as well as climate conditions, such as the changing drought conditions that are expected to emerge. Projects generally rely on nature-based and green-gray infrastructure, as natural features are often modified to enable targeted movement of surface water into aquifers. This slide shows a managed aquifer recharge project funded in support of the Yakima Basin Integrated Water Management Plan and ground storage system. From the outset, they took an adaptive approach. It began with a basin-wide assessment to identify aquifer storage and recovery, to identify recovery of irrigation canal seepage, and to identify surface infiltration projects. After that basin-wide assessment, they came up with a list of 80 projects. But critically, the project developed several monitoring projects within tributaries, ditches, and wells. And the monitoring component is the critical component that will allow adaptive manage because it details how much water is moving into the aquifer and at what rate. And so monitoring over time will help identify whether the emerging drought conditions are getting worse and are affecting the ways at which the projects that are in place and that could be put in place are performing. So that brings me to the end of the 3 examples I wanted to talk about. In a moment, I'm going to pass this discussion over to Jane Aaron. What I've done is I've highlighted several climate risks identified in NCA 5. I provided some project examples that show innovative and emerging environmental projects that incorporate approaches to reduce climate risk for site-specific projects. And the examples demonstrated steps from vulnerability assessment to project design to implementation of adaptive management. Jane Aaron is an expert in systemic risk reduction. What she will do is she will discuss climate risk from the perspective of a portfolio, whereas I talked about a specific location and how you might manage a specific location. Her interest and her expertise is in the area of what happens when you have multiple locations, multiple assets that you need to manage at the same time, and they're all experiencing the effects of climate change. Jane, take it away.
Thank you, Chris. Again, I will be talking briefly about a systematic considerations, and I will be using the Department of Defense in my example. The Department of Defense, or DoD, have been looking at climate change for a while now to determine how climate change poses threats to national security, military mission, and their readiness. In 2016, DoD enacted Directive 471521, Climate Change, Adaptation, and Resilience, which requires the military to consider climate effects on mission and to implement procedures to anticipate and manage risks to build resiliency into the agency. In 2018, Hurricane Michael damaged every building at Tyndall Air Force Base, affecting overall installation operations. Then later in 2018, Hurricane Florence flooded 3 Marine Corps installations. These 2 storms alone resulted in more than $8 billion in repairs to critical infrastructure and assets. Climate change can also affect DoD's readiness in other ways, particularly in the area in their ability to train. Severe drought and heat, for example, can result in loss of vegetation, increase in wildfire, and more dust. This can limit live fire training exercises or restrict low-level rotary aircraft operations and can cause heat exhaustion and other health issues for trainees. Next slide, please. In one program area, natural resource management, DoD developed a guide to incorporate climate strategies into their integrated natural resource management plans. DoD also has responsibility to manage cultural resources, and they have a lot of them. Through the DoD Legacy Program and using the Natural Resource Guidance as a model, we developed the Climate Adaptation Guide for Cultural Resources. This guide includes an overview of climate risks to military installations and mission and cultural resources, and provides climate adaptation strategies and actions to address the risks. It also has step-by-step methods for going through the adaptation planning process and integrating the outcomes into an integrated cultural resource management plan. Part of the planning process is the vulnerability assessment, which Chris just described earlier. This slide shows a few examples of climate impacts to cultural resources and possible strategies. These impacts can also affect other resources, health and safety, and infrastructure. One classic example of a reduce vulnerability strategy was the moving of Cape Hatteras Lighthouse inland. We're also seeing raising buildings onto taller foundations above projected future flood levels as another reduce vulnerability strategy. Next slide, please. Some of the takeaways, considerations, opportunities that we learned from developing this guide: climate change is not an action that triggers Section 106 under the National Historic Preservation Act. So for most federal agencies, it is hard to justify and secure funding for projects solely focused on reducing climate change effects to historic properties. For all agencies and entities, a more successful approach is to develop strategies for cultural resources that support the agency's overall mission and operation and benefit other resources. Working within other departments or program areas to integrate strategies across multiple program areas is a more systematic approach and more economical and efficient. This collaborative approach will hopefully avoid unintended consequences as well, such as cutting a fire break through an archaeological sensitive area or removing historic fabric from historic buildings. Engineering with nature type projects provide a lot of possibilities for benefiting cultural resources as well as other resources and critical infrastructure. Now I will turn the presentation over to John to talk about mitigation.
Thank you, Jane. Next slide, please. Climate resources are really a good example of the perennial challenge of the tragedy of the commons. There's been a historical absence of costs or penalties, creating a negative externality, which enables overuse of the resource and consequent loss for society. As our previous speakers have indicated, the effects of climate change are already being experienced, and they're expected to increase. On the current GHG emissions trajectories, atmospheric warming is likely to exceed 2 degrees Celsius above pre-industrial times, causing potentially irreversible climate effects. This has led to a fairly wide acceptance of the need to reach what's called global carbon neutrality by mid-century. Attaining this goal will require aggressive mitigation. As I think Chris Anderson made clear, adaptation and mitigation must go hand in hand in order to succeed. Next slide, please. So more specifically, when we talk about climate, mitigating climate risk, what do we mean? So mitigation is basically a two-element idea. The first is reducing the flow of greenhouse gas emissions to the atmosphere, and the second is increasing the rate at which the GHG are removed from the atmosphere. And fortunately, there are some anthropogenic and natural pathways for both. Just as a reminder to folks on the call, here's some examples of anthropogenic GHG sources. We know that when we burn fossil fuels like coal and petroleum, we emit carbon dioxide, methane, nitrous oxide, and black carbon. We know that there are significant fugitive emissions of methane from animal agriculture, from oil and gas production, and from solid waste and wastewater treatment. With black carbon, globally, most of that arises from cooking and home heating with solid fuels, which is not as common in the developed world as the developing world, but it also includes open burning and forest fires. And finally, release of high global warming potential engineered materials like hydrofluorocarbons, sulfur hexafluoride, nitrogen trifluoride, etc., are an issue. Next slide, please. The listing you see here are examples of mandatory GHG reduction vehicles or frameworks. The first four bullets refer to control technology programs under the Clean Air Act. Those basically are control technology-based programs that specify a level of control for greenhouse gases. It's a traditional command and control type of regulation. The next two bullets refer to the recognition that hydrofluorocarbons, HFC, originally conceived of as a substitute for CFCs and HCFCs, which have higher ozone depleting potentials, has been determined to itself as a category have very high global warming potential. So between the international agreement, the Kigali Amendment to the Montreal Protocol, and the US regulation under the AIM Act, these materials are being phased out. There are also a number of states that are unilaterally regulating things like greenhouse gases from the transportation sector or some of the engineered materials. And regionally, organizations like the Northeast Regional Greenhouse Gas Initiative, or RGGI, and the California Cap and Trade System are controlling GHG emissions from multiple sectors. Also, at the national level, the Council on Environmental Quality has issued guidelines for assessing and mitigating GHG emissions associated with federal actions under NEPA. And there's also been the use of the concept of the social cost of carbon at the federal level in rulemaking. And finally, we have various national commitments evolving since COP21. But this just in, as COP28 enters its final stages, the International Energy Agency, the IEA, has found that pledges made to this point in the UN Climate Conference will only amount to about 30% of emissions reductions needed to meet the Paris Agreement targets, while the conflict over the future of fossil fuels remains strong amidst controversial statements from OPEC. It's worth noting, though, that in 2010, only about 5% of global GHG emissions were subject to any sort of carbon pricing framework, and now the number is about 25%. Next slide, please. Okay, I'm going to go ahead assuming there's a slight lag in what I'm seeing, but the next thing I want to talk about briefly is what are called short-lived climate pollutants. There's a subset of GHGs that are recognized to have more profound atmospheric effects in shorter time frames than the one that we traditionally think of, which is CO2. Excuse me. So these midterm effects are important because of this target of reaching carbon neutrality globally by mid-century. The short-lived climate pollutants are estimated to have caused nearly half of the climate warming experienced to date. A third of that effect is attributed to methane. Human activities account for between half and 2/3 of those emissions. And it's worth noting that on a 20-year time horizon, methane is about 80 times more potent than CO2. So on the lower right, you see the US estimate for 2020 of the different sectors where methane emissions are rising. It's worth noting that a number of academic institutions and the International Energy Agency believe that methane losses from oil and natural gas production are much higher than what's estimated by EPA and shown there at a level of 32%. Next slide, please. So we talked briefly about mandatory GHG reduction. There's also voluntary actions that are taking place, and usually it's in response to market pressure from public demand concerning sustainability and anticipation of potential future legal mandates. Various private and government entities are also quantifying their emissions, that is, their carbon footprint, and pledging to voluntarily reduce those emissions. This often occurs as an element of an environmental, social, and governance program, an ESG program. Of late, many organizations are finding that when they do a complete tabulation of their emissions, including Scope 3 or so-called value chain emissions, that the totals they're finding are immense, much greater than anticipated, particularly if you had a history of calculating Scope 1 and Scope 2 only. This will make reaching that carbon neutrality by mid-century challenging. So many organizations have been and are continuing to use carbon offsets from what's called the voluntary carbon credit or offset market. These are increasingly being relied on to enable aggressive projections of reaching carbon neutrality by mid-century. It's worth noting that there's also increasing uncertainty about the sourcing and the verification of these voluntary market offsets. And this will present both cost and availability challenges to users going forward. Next slide, please. All right, this is a kind of a scatter diagram of GHG mitigation strategies. And most of these should be familiar. Certainly, the use of or conversion to renewable energy is an essential element, and we're seeing that proceed at a previously unexpected pace globally, which is a good thing. Of course, we know also that this source of energy can be highly variable, so we need a coincident strengthening of grid storage capacity. Methane capture and use. One of the best things to do with methane, because it's a fairly clean and valuable fuel, is to capture it, whether it's natural gas that's leaking in the form of fugitives from natural gas and oil production, or whether it's high methane biogas produced in waste or wastewater treatment. Control of the release of engineered materials, mentioned that previously. That's a particularly important area because HFC in particular is a short-lived climate pollutant. Energy conservation has always been a valuable approach for reducing GHG emissions because the less fuel we burn, the less we emit. Sustainable fuels, particularly in commercial aviation and shipping, are gaining a lot of interest. It's worth noting that the first transatlantic crossing of a commercial aircraft fueled by a biocarbon-based aviation fuel was fairly recently. Industrial process change, I'll talk a little bit about this in a minute, but a number of GHG-intensive industrial processes are being re-engineered because they're difficult to control. Two areas that are important, assuming that our grid continues its progress toward renewable energy sourcing, are building electrification and transportation electrification, and then finally the generalized bucket of carbon capture, which has many aspects. We'll talk about a few of those here shortly. Next slide, please. Carbon capture and sequestration. This was long seen as a potential means of keeping carbon out of the atmosphere without having to re-engineer our industrial society. It's growing slowly, but carbon-intensive industries present a lot of challenges, and you see some snapshots of some of those industries here. Of course, the power industry, the big challenge there is the volume of gas that has to be treated. Portland cement, integrated steel making, and refineries. The technical and economic challenges include the fact that the process streams are not really designed for easy CO2 separation. Commercial outlets for the recovered CO2 are limited, and transportation costs can be significant. So right now, as you see tallied at the top there in the white bar, there are about 30 operating facilities worldwide, 11 are under construction, and 153 are in development for a total capture capacity of 224 million tons per year, which sounds like a lot, but it's pretty small. Attaining the promise of carbon capture and sequestration or storage is going to require the number of facilities to grow by 2 or 3 orders of magnitude worldwide. Next slide, please. The UN Intergovernmental Panel on Climate Change has stated that the negative emissions technology, abbreviated NET, will be needed in addition to GHG emission reductions in order to realize carbon neutrality by mid-century. This photosynthetic biomass is the most common type of negative emission technology. Currently, the cost is about $50 per metric ton of CO2 captured through voluntary reforestation. Next slide, please. This the next slide is a graphic excerpt from NCA 5, and it shows the potential magnitude and the cost of other photosynthesis-based CO2 uptake by both natural and anthropogenic means. Next slide. So finally, we get to anthropogenic intervention. So with the hope of limiting atmospheric temperature rise to either 1.5 or 2 degrees Celsius, that's waning fast with the realization that mitigation is moving too slowly. Technologies that were once considered on the edge and somewhat theoretical are receiving more attention. On the left, you see direct air capture, and this is using well-established technologies to chemically remove CO2 from atmospheric air. The big challenge there is the challenge of scale, because the atmosphere itself contains CO2 at only slightly over 0.04 volume percent. Currently, there are roughly 20 of these DA systems operating worldwide, but they're only capturing less than 1 million tons a year of CO2. So the expectation is that their growth will accelerate as the growth of solar PV and wind generating accelerated, but right now the cost per ton of CO2 removed is between 250 and 600 US dollars. Finally, we look at solar geoengineering. Many of you, I'm sure, have heard the term geoengineering. This is the deliberate, large-scale intervention in the properties of the atmosphere to alter the energy balance of the planet. The first and most prominent example is scattering stratospheric aerosols. We know from recent experience with volcanic eruptions that in fact does cool the atmosphere for a period of time. Of course, this would have to be an international initiative, and the potential for unintended consequences is a sobering aspect of this at this point. So now I'm going to turn it back to Dan Walker for a wrap-up. Dan?
All right, thank you, John. All right, so I know we've given you a lot of information, a lot to think about. Of course, this is a complex topic to begin with, but there's a few things I really want you to try to take away from this. First of all, as the NCA 5 points out, as IPCC has pointed out, climate impacts are happening now. This is not a future exercise. This is not something that we can, that we're going to plan for in the future. Those impacts are taking place now. The rate of change is accelerating in many instances. So, we're really forced with making some really quick decisions here about how we're going to try to adapt and mitigate climate. Second of all, we've got to move away from small individual projects to the degree possible. We have to take a more systematic approach. We need to look at how the totality of projects that we could undertake in a watershed or along a coastline or in other geographic areas can complement each other and get the maximum benefit possible so that we get that maximum return on investment. And then, underscoring all of this is the more adaptation we have to do, the more it just emphasizes that minimizing the total change in temperature is going to be the real key. And that just brings us right back to mitigation and managing our carbon footprints in a more effective way. So I'm going to turn it back over to Amy, and then we'll try to take some questions.
While people are typing in, Dan, let me jump off with a question. In developing the new guidelines and standards, is ASCE considering both resilience and mitigation during construction, as well as, the final deliverable?
Yeah, that's a great question, Amy. And actually, ASCE is involved in both. I chair the Committee on Adaptation to a Changing Climate, but there's a sister committee called the Committee on Sustainability. The Committee on Sustainability just in the last month released ASCE Standard 73, which is a standard on sustainable construction practices. It provides a lot of guidance about where and how we build projects, gives some options for how to mitigate or manage the carbon footprint during that construction phase, including choices of materials, choices of design, etc. So yeah, ASCE is definitely focused on both aspects.
Thanks, Dan. All right, we'll give it a minute. If anybody has any questions, feel free to put them in chat. Well, with no further questions, we're going to wrap up the webinar. Wow, right on time. Thank you again to Dan, Chris, Jane, and John for such great information. Please watch for an email from EA News, and feel free to reach out or visit our website for more information. Thank you all.